Everything we've been learning so far here in Unit 8 on the behavior of gases has been, for the most part, a comparison of one gas to itself. And what I mean by that is in the ideal gas law, it is what are the conditions of the gases at this very moment. In the combined gas law, that is what were the conditions versus what they will be, sort of a change in time, right? A change of sorts. What we're going into now is sort of starting to compare one gas to another gas. And this is going to culminate in something called gas stoichiometry, but we're not quite there yet. So the first thing we need to understand for something called Avogadro's principle is that an equal volume of a gas, if they are at the same temperature and at the same pressure, they're going to contain, I'm going to do this shorthand, okay? I'm sorry, guys, but I don't want to, it's kind of hard for me to write on the screen all the words, but basically an equal number of molecules. Okay, again, that's just shorthand for an equal number of molecules. So it doesn't matter if we're dealing with like the smallest gas of like say helium and a much, much larger gas of many elements put together into a gaseous compound. If they're at the same temperature and if they're at the same pressure, we can assume that the number of molecules in that volume would be absolutely identical. Okay, that's Avogadro's principle. So the way we're going to do the math is a very simple cross multiplication like this. We're going to compare the volume of something over its number of particles or moles equal to the volume of a different compound, a different gas, over its particles or moles. Okay, so let's try this out. Number 5, it says, if a 5-liter sample contains 2.00 times 10 to the 23rd molecules, how many ammonia molecules would be in a 5-liter sample at the same temperature and pressure? So what I'm going to do is I'm going to take my first condition, my compound A, if you will, which is oxygen, and I'm going to put 5 liters right here on as the numerator. Underneath it, I'm going to put its quantity. Now, mole is a quantity and molecules is a compound, but notice we're given a lot of molecules. So in this particular case, I don't actually have to convert molecules into moles. Now, the reason is because we're given many molecules, plural. If we were given a molecule, well, yeah, I can't really make that comparison, but in this particular case, I can. So here I'm going to have 5.00 liters. Again, that's referring to the second compound, which in this case is ammonia. And we don't know our number of molecules. So this is pretty simple. I'm just going to do a cross multiplication. So I'm going to do the bottom left to top right because I have both my variables. That will be my numerator. So 2.00 second E, 23 times 5. I'm going to divide by my short diagonal. So divide by 5, and you guys probably already figured it out. It is the exact same answer. And that is, again, just to show you that if we have two different gases, in this case, oxygen and ammonia, if they're at the same temperature and pressure, then not surprisingly, it is the exact same number of molecules, regardless that it is a different gas. Okay, that again is the theory behind Avogadro's principle. Now, if we start to tweak the numbers just a little bit, you'll notice number 6 and number 7 look surprisingly similar to number 5. There is a little difference, but it's pretty minor. So let me change my colors because, you know, I like to be fancy. Number 6, it says, if a 5-liter sample, so 5.00 liter sample, contains 2.00 times 10 to the 23rd molecules, okay, that's a 3. And that is going to be equal to how many ammonia molecules. So again, this sounds remarkably similar to number 5. The only difference is we're going to change this to 10.00 liters. And again, we're looking for our X. Now, those of you who are good at math or mathematical relationships, you may be able to predict what our answer is going to be. Again, our volume is doubling. So what is that going to do to our number of molecules if they're at the same temperature? And again, if they're at the same pressure? Well, let me go ahead and mathematically determine that. Meanwhile, again, I'm hoping you're predicting in your head. And again, not surprisingly, it is, let's see, 1.0 times 10 to the 24th. That is molecules. Okay. Oh, I did that wrong. I knew that didn't sound right. I'm so sorry, guys. That did not sound right to me, so that is why I just paused and did the calculation. I must typed it in wrong. Again, knowing what the mathematical relationship is, if I double my volume at the same pressure, then not surprisingly, what I should have gotten, but I mistyped it, and again, that's why I knew I was wrong, is because it's just going to double. It's just going to double. So if I double my volume, I'm going to double my number of moles or particles or the quantity of particles in that gas. Again, it always helps if you could calculate correctly, like I did not. All right, I'm going to go ahead and move on to number 7. Again, it's going to be very, very similar to the previous two. So I'm going to go ahead and I have my 5.00 liters. I'm going to put moles this time, not molecules, but moles. Again, it doesn't really matter because we just need a quantity on the bottom in this particular example. How many molecules? Ooh, okay. So that's molecules, not moles, would be in a 10-liter sample. So again, knowing how the way number 6 worked out, again, you guys should be able to figure out what is going to happen here as I verify with my calculator. And yes, this time I did it right because I know that my answer should double. So it's going to be 4 moles. Now, the only difference is I need to convert that into molecules because again, we were given moles and now we want to know molecules. So I need one additional step. So I'm going to do my 4 moles of ammonia, which is NH3. I'm going to put 1 mole down here to convert out of. That will cancel. And then to molecules, I need 6.02 times 10 to the 23rd molecules. Okay, so I'm going to take my calculator. I'm going to go ahead and type in 4 times 6.02 second E 23 divided by 1. And I get my answer. I'm going to put it up above. Sorry, guys, I don't have a lot of space here. 2.408 times 10 to 24 molecules of what? NH3, which is ammonia. So again, number 5, what you notice is that if the volume stay the same, well, not surprisingly, our quantity of molecules or moles is going to stay the same because again, the temperature and the pressure are constant, which again is Avogadro's principle. Number 6, if I double the volume, I double my number of molecules or moles or quantities. Number 7, again, it did the exact same thing as number 6. It doubled the quantity. The only difference is number 7, they threw us a slight twist in that they didn't want us to finish with moles, which is what we originally solved for. We had to go into molecules. So I needed to do my conversion for every 1 mole is 6.022 times 10 to the 23rd. So there's my answer. So that, in essence, is Avogadro's principle. Again, as long as the pressure and temperature are the same, then the volume will, or it's going to be the quantity of the molecules, and the volume will also be the same. All right, I'm going to go ahead and stop there because I don't want to make this too long. So let me pause, and then I will make another video. So here we go.